Hello everyone, this is Shimon Yu from Georgia Tech. Today it's my great pleasure to share some of our research progress in the field of ferroelectric devices. So this is the motivation for our research. As you know that the hardware accelerators for artificial intelligence or machine learning are becoming more and more popular these days. If you look at the cloud applications, the GPU still dominates the training in the cloud, and we see that FPGA is becoming more popular for inference because it can be reconfigured for faster prototyping for different kinds of applications. And also we see that the digital ASIC designed chips, for example, the tensor processing unit from Google, is ramping up both in the cloud and the edge space. So if you look at different technology platforms here, in terms of the energy efficiency, typically is represented in the tera operations per second per watt, essentially throughput divided by power. If you look at GPU, the energy efficiency today is about 0.1 teraops per watt. Similarly for the FPGA, but GPU can support the floating point computation with very high accuracy. And if you look at the digital CMOS-based ASIC design, for example, TPU, the energy efficiency number is about 1 to 10 teraops per watt, and typically they can support like fixed point computation. And here in our research, we want to advocate the computing memory approach, which we try to merge the computation into the memory array. So we can perform some analog computation within the memory array. And with this approach, we can greatly improve the energy efficiency up to like 10 to 100 teraops per watt. Of course, we have to embrace some of the techniques in the low precision computation, and also we may have the concerns whether this kind of analog compute can achieve the same accuracy as a digital approach. To summarize this kind of emerging trend, computing memory, we can say that it can improve the energy efficiency in terms of teraops per watt. And this is especially interesting and promising for the edge inferencing. And also we can enable some of those so-called transfer learning with continuous, possibly unlabeled dataset in the edge devices with this computing memory approach. So in the next, we are going to look at why we are interested in this kind of computing memory approach. Actually, it reflects a shift in the computing paradigm towards this neuro-inspired computing. If you look at our biological neural system, it is composed of synapses and neurons. So the neurons are the simple computing units, and the synapses are the connections between neurons. Or essentially, you can think neurons are the simple computing units, and synapses are the local memories. In the mathematical formulations in the machine learning, so the neuron inputs in terms of the vector, like x, and also the synaptic weights are represented in a matrix, like W. So then we are going to do this so-called vector matrix multiplication between the input vector and the weight matrix. So essentially, it's a dot product process. And after that, we get a so-called weighted sum, and we will perform the activation function on the weighted sum. And this is typically done by the neuron node. So this is the principle of the neuro-inspired computing, where we try to distribute the computations into the neuron nodes and the synaptic elements. So this is different than the von Neumann architectures used in today's computer system, where the data bus will impose a memory wall between the processor and memory, because you have to transfer the data very frequently between the computing and the memory in this kind of conventional approach. While in this neuro-inspired computing architecture, the computations is very distributed. So we have the neurons to do some simple activation functions, while the synapses are carrying the weights. So this is what we try to resemble from the biology, but of course we're not going to mimic every details of the biology. Alright, so this is what we'll try to emulate, essentially. If we have a memory array with this kind of crossbar array, and then each cross point, we can have one memory cell in the form of resistor, or in other words, conductance here. We can try to map the neural network into this kind of crossbar array. For example, the input neuron X will be mapped as a voltage applied to multiple rows in parallel. And then the synaptic weights in this matrix will be mapped as a conductance of those cells in this memory crossbar array. So the voltage multiplied by the conductance will get a current, and we can sum up the current from the column. So at the end of the column, we have the weighted sum current, which will represent the dot product between the input vector and the weight matrix. So the output from the neuron will be the current at the end of the column. Of course, this is analog current. We may need to use some digital analog to digital converters to digitize the partial sum from the memory array. So this is how we accelerate the weighted sum operations, because we can do this computation in one shot, fully parallel. Also, we can change the weight of the memory cell. So that means we have to program those memory cells with the voltages, either row by row or fully in parallel. If you look at what kind of devices that can be applied to the crossbar array to do this kind of computation. So here we are interested in those emerging non-volatile memories. And there are different kinds of memories available. And the first three are two-terminal devices, like those filamentary resistive random access memory or non-filamentary random access memory. So this is based on the oxygen vacancy formation and diffusion in the oxide. And also we may have the phase change memory, where the phase change materials like the GST may go through this transition between amorphous and crystalline phases. So those are the two-terminal devices, and we can directly apply that to the crossbar array. But also we may use these ferroelectric devices, although it's three-terminal. We can use the gate to represent the row, and then the drain to represent the bit line along the column. So still we can use it as a pseudo crossbar array. And in the ferroelectric devices, as you may know that, we can tune the polarization state of the ferroelectric layer in the gate stack to tune the threshold voltage of the channel. So we can still have multi-level states in the conductance. Here, none of the devices are perfect in terms of the synaptic behaviors we may want in the crossbar array. For example, the filamentary R1, the reset is gradual, but set is abrupt. And in the non-filamentary R1, maybe the set and reset are both gradual, but the conductance tuning is quite slow. Phase change memory, the set is gradual, reset is abrupt. So those are not ideal because we want to achieve multi-level states to represent the analog weights in the network. So that's why we are interested in the ferroelectric field effect transistors, which may help to solve some of the challenges in the other devices. So if you look at what are the ideal wish lists for the resistive synaptic devices used in the crossbar array. So here is a table summarizing the ideal specs. For example, we want the device to be as small as possible, let's say less than 10 nanometer, and the programming voltage around 1 volt to be compatible with the logic peripheral circuits. And multi-level states, how many conductance states we can have in the device. Let's say prefer to be larger than 128 levels, that will translate to 6 bits. And also we wish to have a linear and symmetric updates. I will go to this point later. Dynamic range means on-off ratio. The ratio between the maximal and minimal conductance larger than 100, and on-state resistance prefer to be in this range of 100 kilo ohm to mega ohm, because we have to sum up the current from the cordons. We don't want each device to contribute too much current. Otherwise, the cordon current will be too large to be handled by the preferred circuits. So this 100 kilo ohm to 1 mega ohm is a preferred range. And energy consumption to program the weight preferred to be less than 10 femtojoule per programming. And the retention and endurance, this depends on the operation mode. So in the inference mode, where the network is pre-trained, we just do the read operations on the memory array. Then we want the retention as good as non-volatile memory, for example, 10 years. While in the in-situ online training, where we need to frequently update the weight, then we don't need non-retention, but in that case, we need good endurance because we have to update the weights. That means we need to program and erase the weights very frequently. And for typical data set, we need like larger than 10 to the power 6 cycles. Of course, all those numbers depends on the application and what kind of data set you want to process. I would argue that the ferroelectric field effect transistor, FeFET, satisfy many of those requirements here. For example, the unstated resistance, which is the channel resistance of the FeFET, which can be modulated by the gate voltage, and we can achieve in this desired range. While the other devices, for example, the phase changing memory and RRAM, typically we only have like a few kilo ohm to 10 kilo ohm unstated resistance. And also the energy consumption to program the FeFET is pretty small if you think about the scaled FeFET, because the programming is the field driven through the gate. There's no static current passing through. So we can reduce the energy consumption to be just the charging and discharging from the gate capacitance. Then we can reduce the energy consumption to this like femtojoule level. While the phase change memory or the RRAM devices, we have to pass large current to change the state. Then typically the energy consumption is in the picojoule level. All right, so let's move to the FeFET as a candidate for the Synaptic devices. So this is a work that we did together with Professor Sumandata's group from University of Notre Dame. This was published in IEDM 2017. This is like a first demonstration of the multi-level states in the ferroelectric FeFET based synaptic devices. So this is a non-channel device fabricated in the University of Notre Dame. And here we have 10 nanometer HZO, half-length zirconium oxide as a ferroelectric gate stack. And we can tune the gate voltage by multiple pulses to partially polarize the ferroelectric gate stack. So you can partially flip the domains, then the threshold voltage of the FeFET will be changed. So you can see that here is a shift of the IDVG curve, indicating the shift of the VTH state. Later, you can apply a fixed gate voltage here to read out the multiple channel conductance. So we can use that to represent the multi-level analog weights in the neural network. So this is the demonstration by that work. Here we tune the different pulse amplitudes to achieve different channel conductance of the FeFET. And here we demonstrated 32 states, that means 5 bits. And we can have this kind of gradual set and gradual reset behaviors. And this is a corresponding IDVG curve with multi-level threshold voltage, where we extracted the channel conductance. So you can say that we can achieve like tens of levels through the fast programming, like 75 nanoseconds. But still here we use non-identical pulses, which may be difficult from the preferred circuits design point of view. So in the next, we try to improve this design. If you compare different analog synapses used for this on-chip training, we have talked about the filamentary RRAM or this interfacial RRAM and this FeFET. So this is the generic weight update behavior, conductance versus number of pulses. So as you can see that the FeFET tend to improve the linearity and symmetry in the weight update behavior. So this can help to increase the training accuracy. So here is a benchmark for different devices on the MNIST handwritten digits recognition. And you can see that with FeFET, it can improve the accuracy to be 90%. But still here, we use non-identical pulses, which may be difficult to design with the peripheral circuits. And also the 90% accuracy is not as good as the software baseline. Typically is 97% for MNIST dataset. So we want to improve this design, and we add 2 additional transistors here, and then we form this so-called 2T1 FeFET synaptic cell. So here in this case, we have 3 transistors. 2 of them are regular CMOS transistor, and then this is 1 FeFET. So with this kind of design, we can achieve perfect weight update behavior linearly and symmetrically. So with this kind of approach, then we can use identical pulses to increase and decrease the conductance with pretty fast programming speed, and also we can achieve very good accuracy close to the software baseline. So in the next, I will talk about this work in more details, which was published in IEDM 2018. So this is the motivation we designed this 2 transistor 1 FeFET synaptic cell. We observed that the precision requirement in the neural network training and inference is different. So this was done by a 3-layer fully connected multi-layer perceptron network on the MNIST dataset. As you can see that for the training, we need at least 6 bits of the weight to be to achieve the good accuracy, which translates to 64 levels in terms of the conductance of the cell. While in the inference, where the training is done and we just read out the weights and do the prediction, then you can see that 2 bits of the weight is good enough. So this is the observation from the algorithm's point of view. And similarly, there are some other algorithm papers saying that 8-bit training, 2-bit inference good enough for a more complex CIFAR10 dataset. So here, the key idea of this design is to use non-volatile memory to store the most significant bits, MS bits, for example, the first 2 bits, while using the volatile memory to store the rest, least significant bits, LS bits. For example, 6-bit weight, which is required to train the MNIST dataset, will be split into 2 parts. The first 2 bits will be stored in the non-volatile memory, and the rest 4 bits will be stored in the capacitor. So how do we achieve this in the FeFET based design? So here is the key idea. We propose this 2 transistor 1 FeFET with cell design. So here, as you can see, we have 1 pull-up PMOS transistor, 1 pull-down NMOS transistor. So we are going to use those 2 transistors to charge and discharge the gate node of the FeFET. Because we can charge and discharge, so we can modulate the voltage on the gate node. And this voltage will control the channel conductance of the FeFET, where we are going to bias the FeFET to be in the linear region. So then we can fine-tune the gate voltage by this charging and discharging. So we can fine-tune the channel conductance of the FeFET. Here we try to, for example, in this IDVG curve, we try to modulate the gate voltage in this range, where we can linearly modulate the channel conductance. So this can be achieved with fine and linear steps. But as you see that this is represented as a gate voltage on FeFET, essentially on the gate cap. So this is volatile. On the other side, we are going to use multi-level VTH state caused by the partially polarization state in the FeFET to modulate the cost step in this tuning. So this is what I mean by the cost step. So here, for example, we can program the FeFET into 4 polarization states or 4 VTH states. So we have 4 IDVG curves here. And the gate voltage modulation can change the conductance within this range. But if you keep increasing the gate voltage by charging, then essentially it will charge up to here. And that means we are going to carry in the bit from the low significant bit to the most significant bit. That means we have to move up the VTH states from the S0 to S1. So that means we are going to program the FeFET to a different VTH state. Then we can constrain the voltage, gate voltage between the VA and VB node, while the current can be continuously increased. So that means we are going to use those 4 VTH states to represent 2 MSB bits, which will be non-volatile. That means after the training is done, we can only remember those 2 MSB states, and we can use that for the inference. So to summarize here, the gate voltage will modulate the FeFET conductance in fan and linear step through the charging and discharging. And once in a while, we may want to carry in the LSB to MSB. So that means we have to program the FeFET to the corresponding VTH state. And this represents cost step. And this is the non-volatile effect. We can use that to do the inference later. Okay, so we experimentally validated the FeFET on the University of Notre Dame's sample. We can program the FeFET using different kinds of gate voltage to multi-level states. But in this 2T1 FeFET design, we just need 2-bit MSB. That means we just need 4 states from the FeFET. So here we have 4 distinguished states from the FeFET. And then we try to simulate the 2T1 FeFET design through the SPICE simulations. Here we have the FeFET compact model based on a combination of the BSIN4 for the regular MOSFET and the precise dynamic model to model the multi-domain effect in the FE cap. So here the key is to balance the Q, the charge between the FE cap and the MOS cap. So this was published in the VLSI 2018 by Suman's group. So we use this kind of SPICE model and then simulate this kind of behaviors of the multi-level programming, and will capture the experimental data we measured. So here we designed the VA and VB range to be 1.44 volt to be 1.76 volt. If we think the small step by the charging and discharging is 20 millivolts per step, then we can represent 4-bit LSB in this range. Plus 4 VTH states, we can in total get 4-bit LSB plus 2-bit MSB. So this 6 bits good enough for the MNIST dataset. By combining this 2-bit MSB and 4-bit LSB, we can equivalently show this kind of weight update behavior. This is normalized conductance versus the programming pulses. So this is for the positive update. This is for the negative update. We can see that this is pretty linear and symmetric. We can examine the increase and decrease of the weight update by differentiating the conductance versus the pulse number. So we can see that each step, it can only differ by 1 millivolt in terms of the linearity. So we can see this is pretty linear update. One concern we raised earlier is the leakage of the gate voltage. So here we do the SPICE simulations to analyze the decay of the gate voltage through the leakage of those transistors. As you can see here, the voltage of the gate may decay over time, and we found out to decay by 1 LSB step, that means 20 millivolts. It takes like 1 millisecond. So that means we have to finish some computation within this 1 millisecond, and then we do the weight transfer. So we can estimate the transfer interval in terms of the number of batches of the images. So we can estimate it like every 200 batches, and each batch is like 100 images. After that, we need to do this transfer process. That means we need to program the FeFET with this kind of frequency. With this kind of design, then we eventually benchmark the neural network performance on the data set like CIFAR-10, which is essentially image recognition of those 10 classes of objects like dogs. So here we extend the LSB to 5 bits by reducing the voltage step from 20 millivolts to 10 millivolts, because this is required for this more complex data set. With this kind of approach, we can say that the training accuracy can achieve like 88% accuracy, which is close to 90% of the software baseline. So we think this is a good approach to design the neural network on the chip and perform similarly as the software using the 2T1 FeFET design. Next, we are going to discuss some of the array level challenges when we operate the FeFET array to do this kind of in-situ on-chip training for the neural network. Because the neural network requires the weight to have this incremental increase and decrease. For example, when we change the MSB in our 2T1 FeFET design. But if you look at the FeFET array, typically the memory array will share the substrate. And if we erase the FeFET, the conventional way is to apply the positive voltage to the substrate. But then the whole array will be erased simultaneously. This is not good for the weight update incremental change. So we need to explore the individual programming and erase scheme to allow this kind of in-situ training on the FeFET. So here we propose the string erase scheme. And this is a diagram showing the voltage biases we apply to program and erase the FeFET array. And here we skip the 2 additional CMOS transistors in the array. And essentially, here what we will do is to program those FeFET. We skip the 2 transistors in this schematic, but you can add that there. It does not change the essence of this design. And so here we, for example, if we want to program this cell, then we need to apply gate voltage like 3 volts to the FeFET and then ground the source line bit line. And so this is a gate programming. But then the other cells may be in the disturb mode. For example, here the same cells along the row will also receive 3 volts on the gate. So we need to inhibit the programming on the other cells. While in the erase, we don't do the block erase by the substrate. We have to do the drain erase. That means we apply like 3 volts to the bit line and then ground the gate word line, and then according to the channel potential difference between the FeFET here, the channel potential versus the gate potential, then this cell will be erased. However, the other cells will not be erased, but some of the cells are in the disturb mode. Then we need to inhibit the disturb. For example, the cells along the same column will receive 3 volts to the bit line, and we need to inhibit those cells from being erased. So this is the design diagram for the in-situ training to allow individual cell programming and erase. We need to verify this kind of voltage biases through the experiments in the next. So what we do here is to perform the device characterizations on Global Foundries 28 nanometer high-k metal gate FeFET or the 22 nanometer FDSOI FeFET. So we have the experiments done here using the pulse programming mode. This is the voltage waveform we apply on the FeFET. And so here, for example, for the drain erase, we apply a large voltage on the drain, while we have to apply a small voltage on the source and then ground the gate. So with this kind of configuration, we hope that the cells can be erased successfully. So this is a voltage bias on the FeFET. And now we increase the drain voltage from 1 volt to 3 volt, and you can see the current is effectively decreased. So that means the erase is successful in this case. So this was done on the FDSOI devices at 22 nanometer load. And this phase map shows the combinations of the pulse width and the drain voltage to effectively change the conductance of the FeFET. So here you can see that, for example, here we can apply 1 microseconds pulse, but with 3 volt drain voltage, then we can effectively erase. We have to be careful here that we need to apply 1.5 volt to the source to allow this kind of effective drain erase. If we apply 0 volt to the source, then the erase is not effective. And also we verify different W over L. We can see for the large device, this is also possible. For the small device, this is possible. But in the high metal gate bulk devices, the drain erase is not that successful. So what is that? We performed the TCAD simulations to analyze the channel potential when we apply like 3 volt to the drain and then 0 volt to the gate and 1.5 volt to the source. So with the band-to-band tunneling model incorporated, we can see that the channel potential of this FDSOI devices is raised up. So this channel potential is much higher than the gate potential, and due to the Guido effect, we can successfully erase the state. But in the bulk devices, because the channel is not confined, then the channel potential was not raised up significantly, even with the same voltage bias. So that's why in the bulk device, the drain erase is not successful. Later, we also examined the different schemes in the array. For example, here we verify the gate programming, where we apply a gate voltage to the gate while ground the drain and source. So here we see that with the gate voltage larger than, let's say, this 2.4 volt, we can successfully program the device from the erase state to the program state. And also we need to check the inhibition scheme because some of the cells may be under the disturb. So here, for example, if we do the programming, we apply 3 volt to the gate. Then for the columns that we don't want to program, we need to apply inhibit voltage from the drain. So here we examined that we apply 3.2 volt on the gate, and then we want to vary the inhibition voltage through the drain to see whether we can inhibit the programming or not. So here we vary the drain voltage. For example, here from the 0 volt, then the drain will be programmed, not good. But if we apply like 1.5 volt to the drain, then the inhibition will be successful. This is with the source bias 1.5 volt. But if we ground the source, you can see that even though we apply drain voltage here, try to inhibit, but still the cells are programmed because the current increases in this case. And also we verified with the source bias, we can inhibit this for many cycles. For example, here we test the 10 to the power 6 pulse cycles. So still the cells are inhibited without disturb. Similarly, we can characterize the inhibition scheme for different drain voltage. So here this is a similar setup. Due to the time limit, I will skip the details, but this is to verify that inhibition on the drain erase is also successful for many cycles. This is the next slide. We want to provide ovation for the future engineering. So we envision that we can eventually build this kind of 3D vertical channel FeFET with those two regular CMOS pull up and pull down for this 2T1 FeFET design. So here we can see that this vertical FeFET, we can achieve multi-domain because we relax the requirement on the lateral dimensions, where we can use the height of the cylinder here to have enough gate area to have multi-domains in the FeFET to create the multi-level VTH state. So this will be a compact design, eventually suitable for the on-chip training. So with this, I'd like to summarize. We proposed FeFET as a promising candidate to enable the computing memory for the deep neural network training, which requires a high precision weight with linear and symmetric update. This can be achieved by this 2T1 FeFET hybrid synaptic cell. And the FeFET array design requires the individual cell to be programmed and erased without disturbing other cells in the array. So we propose the gate programming and the drain erase scheme to effectively enable individual cell programming and erase. And this was experimentally demonstrated on the 22 nanometer FDSOI FeFET devices. And then eventually we envision that we can build a vertical FeFET array to enable this 2T1 FeFET based design. With this, I'd like to thank my collaborators, Professor Sumandata and Professor Asit Khan, and all the students and sponsors of this research. Thank you.